Hi everybody, we're going to work on section 4.3, the product rule, example 6. It says when the price is P dollars per widget, the demand for widgets is given by Q is equal to 100 times 2 to the negative P. Then it asks us to find a formula for the rate that the revenue is changing as a function of price. So the rate that the revenue is changing is R prime. In order to take the derivative of the revenue, we're not given the revenue function, so we need to create the revenue function first. We learned a while ago that revenue is price times quantity. Price is P, and the quantity is the function that they gave us, so 100 times 2 to the negative P. Now notice that our function is two functions being multiplied together. So we're going to need the product rule to take the derivative. So we have two pieces, 100p and 2 to the negative p. Let's set up our two different pieces. So we'll call f 100p and g 2 to the negative p, and we'll take the derivative of each of those. So 100p has derivative 100, and 2 to the negative p. The p is in the exponent, so we're going to use an exponential function derivative. Copy and paste ln of the base times the derivative of the exponent. And then we can simplify that to be negative ln of 2 times 2 to the negative p. All right, so we got all our pieces for the product rule. Now we can take the derivative of the whole function. The product rule is f prime g plus fg prime. So we're going to plug in all of those pieces that we found above. So now we're ready to factor our answer. We want to find out what the whole first piece and the whole second piece have in common. So the first thing I notice is they both have 100. And they also both have 2 to the negative p. So I'm going to factor both of those things to the front. And then we can figure out what remains. So for that first term, we took everything out of it. So what we'll need to put there as a placeholder is 1. For the second piece, we took out the 100 and 2 to the negative p, but we still have the negative ln of 2 and the p remaining. All right, so now I'm just going to rewrite that to where we don't have a negative in the exponent, and then I'll also rewrite it so that that plus minus becomes just minus. So once I drop 2p to the denominator, it no longer needs the negative. And then, as I mentioned, instead of plus a negative, that's just minus. Okay, and I put ln of 2 in parentheses so that I know just the 2 is in the ln, the p is separate. So ln of 2 times p. All right, that was the end of that example. Now moving on to example 7, it asks us to use the first derivative test to find the max and mins. The first derivative test is what we did in section 5.1, but the reason that this is in this section is our function is t times e to the t. It's two functions multiplied together, so we need the product rule to take the derivative. All right, so we're going to start our chart. We'll let f be t and g be e to the power of t. We'll take the derivative of t, which is 1, and the derivative of e to the t. The t is in the exponent, so we use the exponential derivative formula. And once we simplify it, we just get e to the t. All right, now we can use the product rule, which has formula f prime g plus fg prime, and we'll fill in our pieces from above. Now we can factor. We notice that both terms have e to the t, so I'm going to factor that out to the front, and I'm left with 1 plus t. Again, we need that 1 there as the placeholder. From our derivative, now we'll figure out the stationary and singular points, so where the derivative is 0 and where the derivative does not exist. There's no denominator in our derivative, so our singular points, there's no work to do, so we have no singular points. The stationary point is where the derivative is 0, so I'm going to set that whole derivative equal to 0. If two things multiply to be 0, we're going to set each piece equal to 0. E to the t is 0, 1 plus t is equal to 0. Now notice this is a graph of e to the t. It looks like it gets super close to 0, but it never actually hits 0. So that's true for our exponential functions. They never equal 0. So we're not going to get any stationary points from that part. On the other hand, we still have 1 plus t equals 0, so we can subtract 1 from both sides and get t is equal to -1. So our only critical point was that -1. We're going to graph that on our number line. So we'll have -infinity to 0, and we're going to graph or plot our critical point -1. Now we're going to test a point in each of those intervals into the derivative, because the derivative tells us the slope, which tells us if it's increasing or decreasing. So I picked a -5, I plug that into the derivative. If you want, you can plug that whole thing into your calculator, or you can use some reasoning to say my exponential function is always positive, and 1 minus 5 is negative. So a positive times a negative is negative. We got that the derivative is negative on that interval, so that tells us the original function is decreasing on that interval. Now I'm going to pick a point between -1 and 0. It has to be in that interval, so I'm going to pick -1/2 and plug it into the derivative. Again, you can either plug it into your calculator or reason through it that an exponential function is always positive, and then 1 plus -1/2 is positive. So if our derivative is positive on that interval, that means it has a positive slope. So it's increasing, like the original function is increasing on that interval. Now we can go through and find the max and mins, but let's do a little sidestep and talk about the endpoints. So whenever you have positive or negative infinity, you will never have a max or min there. However, whenever you have a number, like 0 or 5 or whatever it is, a number as an endpoint, that will always be either a max or a min. Okay, so if we go back and just look at our chart from left to right, we started out decreasing, and then we changed directions and started increasing. So that looks like a minimum value. And then we're increasing to our endpoint because our endpoint was 0. So that endpoint looks higher than the points around it. It's a max. So we have a minimum at x is -1 and a max at 0. Okay, so we want to put our answer in coordinates. We will utilize the original function to plug in our x values to get the y values. And that'll give us the points -1, -1 over e, and 0, 0. So now we can just fill in our answers for all the work that we showed.